Okay, so section 4.6 deals with rank, and it comments that with the aid of vector space concepts, this section takes a look inside a matrix and reveals several interesting and useful relationships hidden in the rows and columns. Okay, and it turns out that there's a column space, and there's another concept called row space. Okay, so column space is a space spanned by the columns of a matrix, and a row space is a space spanned by the rows of a matrix. Okay, so normally we deal with column space, but row space is yet another idea. And so, all right, I'm going to highlight this. So if you have an n by n matrix, every row of matrix A has n entries, okay, and can be identified with a vector in Rn. But the set of all linear combinations of the row vectors is called the row space, and we denote it by row of A. And the row space, each row has n entries. So the row space is a subset of Rn. Now, one moment here. I think there's a typo there. Hold on. No, that's right. No. Wait a minute. Yeah, that would be right, because the number of columns in the matrix A, if you look sideways at, like, in example 1, matrix A has 5 columns, and so or 6 columns, I should say, in example 1, and so the row space of the matrix A would have to be a subspace of R6. Okay, so that's right. And what they're doing is they're writing down what are called row vectors. Oh, now wait, hold on. Do I have this right? I'm sorry. Example 1, there are 5 columns. 5 columns in example 1. And so the row space would be a subset of R5. And since there are 4 rows, you have 4 row vectors, but each of the row vectors lives in R5, and the row space of A, as it comments here, the row space of A is a subspace of R5 spanned by the row vectors. Okay, it's really that simple. It's that simple. And okay, okay, here's an important piece of information. Okay, so remember how if you're given a matrix, and you're looking to find a basis for the column space of the matrix, and you would do row operations on the matrix. We talked about this last time, and reduce the matrix in reduced row echelon form. Well, the pivot columns of the reduced matrix would correspond to the column vectors of the matrix A that are going to be the basis for the column space of A. So the row operations preserve the linear dependence relationships among the column vectors of A. However, in regards to row vectors of A, row operations actually change the row dependence relationships. Okay, it will change that. So it doesn't work for the row space. But there's a theorem that demonstrates that it's still helpful to do the row operations, because Theorem 13 says that if you have two matrices, A and B, that are row equivalent, then their row spaces are the same. See, that's not true for the column space. The column space, if you have two row equivalent matrices, the matrix that's in reduced echelon form, the pivot columns will determine the column vectors of the matrix A that form the basis for the column space. Okay, but you have to then go back to the matrix A to pick out those column vectors. But for row space, it turns out that the resulting matrix in reduced echelon form, if the row vectors that you get will determine are going to actually be in your row space of A. It's really a fascinating concept. If we look here in example 2, okay, in example 2, they want you to find bases for the row space, column space, and null space of this matrix. Okay, row space, column space, and null space of the matrix. So of course you have to do row operations to get the matrix in. Well, you could do. You don't really have to get the matrix in reduced echelon form. You could just get it in echelon form, right? Because all you need to do is, for the column spaces, identify what the pivot columns are. So they do that. They do that. And so if we go to the next page, they reduce the matrix A to the row equivalent matrix B right here. And based off of this, you can identify a basis for the row space of A. The basis for the row space of A is just the first 3 rows. It's the first 3 rows. Okay, because those rows have, I want to say, like pivots in the rows. I want to be careful. We usually say pivots in the columns, but if you were to flip the matrix up, flip B like up, so that the rows are the columns, you would definitely identify this basis for the row space. Okay, that's what you would do. If you were to look at the transpose of the matrix B, then the row vectors of B become the column vectors of B transpose, and then it's easy to identify this as the row space. Okay, are there any questions on that? I want to make sure everybody's comfortable. All right. Well, on that note, let's continue on. So, which columns in the reduced in echelon form matrix B, which columns correspond to the pivot columns? There are 5 columns there. Which columns are your pivot columns? Which columns are the pivot columns in matrix B at the top there? Okay. Well, it's going to, okay, good, okay. A very good defining, very good, Catherine. Columns 1, 2, and 4 are pivot columns. And for the column space of A, then, what we have to do to identify that, we have to go back to the original matrix, and the columns 1, 2, and 4 are going to be the basis for the column space of A. And so there you go. There's your basis for the column space of A. Okay. And then, of course, the null space, well, now wait. You know how to find a basis for the null space of A. But there you actually have to solve. You have to solve a system of equations. And what they do is they reduce A. They actually get it in reduced echelon form. They go all the way. Okay, and then you get the corresponding system of equations, and you can solve for the null space and get your basis. So you've done that before. I'm not too worried about that for you. But let me ask you, what's the dimension for the null space of A? What's the dimension for the null space of A in this problem? You see there, or do you have a basis for the null space of A? Good. It consists of two vectors. The dimension of the null space of A is 2. Good, Nafani. Good, Benjamin. Okay, well, all right. Very good. Very good. Now, what's the dimension, if we look at the basis for the column space of A, what's the dimension for the column space of A? 3. Good, Nafani. And 3 plus 2, by the way, equals 5. So the dimension of the column space of A plus the dimension of the null space of A will equal the number of columns in the matrix A. Okay, and that reinforces what's called the rank theorem. And I'll note here too, the basis for the row space of A also consists of 3 vectors. So the basis, the basis for the row space of A, if the basis for the column space of A has 3 vectors, so does the basis for the row space of A. They're always the same number of vectors in their bases. But we learned something, we've seen this twice now, this coincidence that the dimension of the null space and the dimension of the column space of a matrix add up to the number of columns that the matrix has. So that's called the rank theorem. That's known as the rank theorem. And incidentally, the dimension of the column space of A is called the rank of the matrix A. That's what the dimension of the column space is. Okay, that's called the rank. So I think what I'd like to do, well, first of all, are there any questions? Okay, well, let's go ahead here. Hold on, I thought I got it down. Let me download a file here. One moment. One moment, class. I thought I downloaded it, but guess I have not. Let me see, where did I thought I did. Hold on, class. I thought oh, there it is. There it is. Okay. Okay. Okay, so I'm just bringing up a file. There's a few nice examples I want us to look at. Okay, let's look at a few examples here. Let me give you a moment to copy this example down. Okay, so I'm going to write here, of course, the rank theorem, dimension of the column space of A plus the dimension of the null space of A equals n. And we're assuming we have an m by n matrix. So the dimension of the column space of A plus the dimension of the null space of A equals n. And incidentally, the dimension of the column space of A is known as the rank of A. So if you have a 6 by 9 matrix, could that matrix have a two-dimensional null space? And naturally, you're going to use the rank theorem here to try to help you answer that. But let me give you a moment to think about it. Okay, so of course the answer is going to be yes or no. And we really have to think about the possibilities. So let me ask you, if a matrix has a two-dimensional null space, what would the rank be of the matrix? N equals 9. If you have a two-dimensional null space, what would the dimension of the column space be based on the rank theorem here? That's right, Benjamin. It would have to be 7. It would have to be 7. Okay, so the dimension of the column space of this matrix would have to be 7. Okay. Is it possible that the dimension of the column space could be 7 for a 6 by 9 matrix? Benjamin doesn't think so. Nafani doesn't think so. Why? Okay, hung 6 rows. So that means the column vectors. So we have a 6 by 9 matrix, 6 rows, and Nafani's right too. The column vectors have to live in R6. They have to live in R6. Well, so what's the maximum number of vectors that, if you're in, I want to be, okay, Eleanor, you have the right idea, 6. You have the right idea. Let me show the solution, but you're all thinking right. You're all thinking right. Okay, here's the formal solution. So let's suppose that you have a 6 by 9 matrix, and we'll call it matrix B. If it has a two-dimensional null space, then by the rank theorem, the dimension of the column space of B would be 7. We're comfortable with that. Why is that? Because 7 plus 2 equals 9. Okay, so let me let you copy up to here, and then I'll continue. I don't want to get too far ahead of you. All right, so we agree that the dimension of the column space of B is 7. But the column vectors in B live in R6. They live in 6-dimensional space. And this means that the dimension of the column space of B cannot exceed 6. Okay, you cannot exceed 6. So in other words, if the dimension of the column space of B is 7, well, if the dimension of the null space of this matrix B is 2, then the dimension of its column space of B has to be 7 by the rank theorem. But since the column vectors live in R6, the number of vectors that would form a basis for the column space can't exceed 6. I mean, if you think about, I want to say this the right way. Hold on. I mean, you know, you could have in the matrix B, you could have the dimension of the column space could be smaller than 6, right? If you had column vectors of B that were linearly dependent. But if the column vectors of B are not linearly, if they're all, I'm going to say this the right way, the most number of linearly independent column vectors that you could have in this matrix B is 6, because the vectors, the column vectors of the matrix B all live in R6 space. So the rank of B cannot exceed 6. It can't. So you'll never get to 7. You see, you'll never get 7 for the dimension of your column space. Does that make sense, class? Is that okay? You have to let me know if you're uncomfortable. Okay, Hung's comfortable. All right, Eleanor says it makes sense. Good, good. Sometimes, you know, it's just sort of, you just kind of picture it in your mind. But it takes time. I mean, it takes time to be comfortable. But the point of this kind of exercise is to help reinforce the ideas behind the rank theorem in section 4.6. Okay. All right. So what I'd like to do, well, are there any questions? All right, let me stop the recording.